This is this is a part of the presentation for the 20 fundamental problems, but actually this is the 21st problem, I think, and because we're adding problems to it, and also we have worked all these other problems, but not this one. No. It's the efficiency proof. No, this is different from what I have on.
Can you state the 21st problem?
It's the efficiency proof.
Okay.
Yeah. So, but it's becoming, the reason that I wanted to present this first is because it is important, and it is like something that I'm working on recently. It connected a few things together. So the past result we could present later. And so today is my presentation. Next week, Dugan's, Empire's rays on the comparison between QSN and 36 vertex type QC, and then Cynthiana's shell model.
By the way, did Ray show you yet the what you wanted to see on the question of the 20 groups at the vertices of?
No.
Okay.
You still owe me that.
Yes, it's on my computer.
No matter how much we trust you, you have to show me. Okay, so so this is like the whole purpose of this presentation covers quite a few topics, but it is all kind of like the general purpose is to find the efficiency proof. Achieve the efficiency proof. So this is a part 1, and so I'm not done yet with the efficiency proof. So part 1, I will cover quasicrystal vertex types and the frequency, empire and the density, coordination number, and the efficiency. So that pairing up, the relationship is like this. This is outline. So we'll talk about the quasicrystal vertex types and their frequencies and how to calculate them. And then quasicrystal empires and their densities. So when we talk about empire, we want to know, if the empire is dense or sparse. And then later on, of course, we talk about the interactions between vertex types, and then I would kind of related to these two properties.
Will you be having a beginning slide that speaks to the motivation?
Motivation of what?
Of the exploration.
The motivation I already said is for the efficiency proof.
Oh, yes. So I'd like to make just one sentence or two about the motivation, since this is a problem that I pushed, and then Fang became more interested. And so just a simple concept. In a quasicrystal dynamic space, your fundamental object can be understood as an expression of transdimensional tension or curvature, right, as we know now. So each edge, whether it's the edge that's the 1 or the edge that's the 1 over golden ratio, in both cases, they're just two different expressions of spatial curvature from a higher dimension. So what you're doing in an animation of 2 or more state selections on a QC possibility space is you're painting a kind of fluid dynamic pattern in some sense, or discretized pattern with curvature. But what's interesting is that it must be conserved. That is, the vertex types must be conserved over any dynamical flow pattern. The volumes must be conserved. The edge contractions must be conserved. In other words, the curvature must be conserved globally. So I think that's a pretty cool first principles geometric fact that sounds very reminiscent to conservation concepts, that we're familiar with in physics.
Okay. And then the last part is, I believe using these two that can help us to calculate the average valence strength of the quasicrystal and their correlation to the efficiency of the network. Because we were talking about the network, the efficiency is kind of proportional to the average coordination number, but somehow inversely proportional to the number of words, letters, actually. Yeah.
Is it? Would you still say it's divided by the quantity of letters?
Yeah, but I don't know if it's that kind of a linear relationship. So that's the same meaning, inversely proportional to that. Okay, so first the quasicrystal vertex types. And then it's important to know that the vertex types are close under inflation deflation rules. Like if you inflate a vertex, it becomes another one, kind of like that. But you don't following the inflation deflation rules of that particular quasicrystal. You don't generate new vertex types. And it's limited by the cut window, because like depending on what your cut window is, the shifted vector, the size, and then you can have different vertex types that we all know. For example, the Penrose tiling and the generalized Penrose tiling have different vertex types. So, and then it can be categorized by the solid angle distribution or the on-off selection of the connections. So for example, the solid angle is for 3D, but in 2D it's just the angle. Depending on how, if you have like 10 directions, basically 10 edge set, and then so you can, depending on like however many connections total, like these are the edges. And so depending on if these on and off connection means you could remove this and remove this, right? And also that also tells us we're using these angles, right? So the distribution of that kind of angle.
Is a solid angle the
cone angle, the
cone.
3D, yeah.
Okay, so it's not the dihedral angle.
No.
It's an angle between.
No. It's a volumetric angle.
So it's an angle between two volumes as opposed to a dihedral angle, which is an angle between two planes.
Yeah.
Think of an angle as like the amount of length that goes around a circle. You can think of a piece of a wedge of a sphere. Look at the surface area of that. That's a solid angle. So you think of the surface area of the sphere in angle terms.
Okay.
Yeah, like this is like what do you call this? Is this like for solid angle? The total is also 360.
4p.
4.
4p.
Oh, 4p. Yeah. Sorry. Yeah, of course. And so which is the surface area of this. And so then you calculate this area, and this area would be the solid angle of this cone there. So, yeah. Anyway. So first of all, I just mentioned a little bit about inflation and deflation. Using the inflation deflation method for the vertex types in Penrose tiling. So most of this talk would use Penrose tiling as an example, because I'm preparing for this, I didn't have time to prepare for the 3D one. So these are the familiar vertex types, the 8 types of vertex types in Penrose tiling, and these are their names, kind of categorized by the symmetries. So you can see this and this. This would be the sun, this would be the star, I think. Actually, this is the sun, this is the star. So, and in closed end inflation deflation, it's actually stated here like, like if we start from this one and then we do I think it's called a deflation. Yeah, deflation, meaning subdivided, and then we can get this one. And from here we can achieve this one. And just like these 4 vertex types, basically from one you can, through deflation, you can get another one, and then similarly the other 4, like, you can transfer one to another. It's not just one and then this one. Of course, there is partially other vertex types too, but just saying like that specific vertex will become like that specific point for 433, that point, when you do a deflation, it will become this. That's what I mean.
I hope I'm not the only one who doesn't understand why, but I understand inflation, deflation, but I cannot understand how that's connected to that 433 becoming 422.
It's not that easy. It's 422, 433. There's lots of typo in that paper. 442.
Or any, meaning it just doesn't matter what two. I understand how you can move your cut window from, and that
no, it's not a cut window. This is a completely using simple inflation deflation, because you could I don't know if I have that page here. I might not have the page. Like this tau, for example, you can subdivide it into a dot and a kite and a dot.
Oh.
And then from the kite and dot, you can subdivide it into rhombohedral.
Oh, okay.
So it's a two-step.
I understand.
Yeah.
I was focused on subdividing the lines, not the areas.
No.
Can I say the thing that I always love everybody to memorize? The fact is that those 8 vertex configurations globally are conserved such that the average vertex configuration in the infinite Penrose tiling must always be 4, which is the same as the average vertex configuration in the Z2 lattice, the checkerboard. And secondly, if you recognize that the top 2 vertices have the same geometry, but they're different vertex types because they have different tiles around them. So if you then recognize those 2 as the same geometry, and you combine their frequencies, then you can order the 7 vertex types to be the values 1 over phi, 1, phi, phi squared, phi, all the way up to phi to the 5th.
These ones.
Yeah.
Yeah, so 1, phi. But these 2 would be the same.
Well, there's another way that I've written it. I pasted it on the board at one point 6 months ago, where it ends at phi to the 5th. That's an accurate way to write it as well, but it's a different way to calculate. But the shortest, most kind of compact expression with the smallest exponents is it goes up to phi to the 5th. So it's a really beautiful series.
Yeah.
On the preceding slide, so I don't know if everyone has understood the meaning of the numbers here, or someone need an explanation?
I don't need it, but I know that they're coordinate numbers, right? And that we use in crystallography, like, right, Fang, like when we do
I can give it now. Now I figure out what it is. It's
sure, okay.
The sum of the numbers is 10.
And the second one is 4, 4.
It's 442.
No.
Yeah, this
Yes,
is
right.
442.
And in fact, it is
the
encoding
angle.
the number times 2 pi over 10 for the angle.
Yeah, it's the
Yes.
angle here.
So 4 is a large obtuse angle, 3 is a smaller angle,
Oh, divided by
1 is a
4.
very small. It's
Yeah.
2 pi divided by
2 pi.
10 for the 1.
Okay.
So it's very
Like
clear,
that's why
but-
it's a 5,
yes.
5, 5, 5.
Yeah.
It is why I said it's
cool.
a categorized by a solid angle distribution. You know, like so. For 2D, it's really simple. For 3D, it's a little bit. It'll be more a little bit. I think for 3D, it was subdivided into. I forgot. It's a 36. Anyway, I don't want to say a wrong number, but yeah, for 2D, it's kind of simple. Okay, so and then so also that kind of like angle distribution, the categorization by angle distribution, like just as Ray explained. And then here it can also be thought as what Klee always mentioned, like on off selection of the connections. Like if you turn this connection on, this connection on, these on, then you get these kind of tiles. But this connection would be off. So this is how the way of kind of categorizing it.
So, and I always like everybody around here to think of the word possibility space. So a possibility space should be understood as having no connections whatsoever. So it's a disconnected graph space. And this is really the smallest graph space that can be fairly called a finite portion of the Penrose tiling, which represents the symmetry of the Penrose tiling. And it's really just the projection of a single 5 cube to the plane, where the 32 points of the 5 cube become 31 points in the projection. And in the Penrose tiling, there are only 12 legal ways to draw your graph connections on this possibility space of red points. And 2 of the 12 are the 2 orientations of the left figure, which, as you can see, can have the star rotated in one of 2 ways only. And then that's composed of 5 thick and 5 thin ROMs. And then the other one has 10 configurations of the cartwheel tiling, which is also 5 thick and 5 thin ROMs. And in each case, you can look at it in a binary fashion, where you turn 15 of the 31 points off in each of the 12 state selections on the possibility space, and of course, the other 16 will be on. So it's 16 ways you can turn points on.
Okay. And so these the frequencies, now I'm not going to talk about the vertex type frequencies. And so the frequencies can be derived by inflation-deflation rules. And Chris Henley did a good job on that, but he didn't explain it clearly, and he had many typos. So I'm not going to cover it here today, because I didn't have time to get all the steps. Otherwise, I cannot make you understand it clearly. Just like even here, you were having a little bit of problem. So I have to kind of have the illustrations for that part. And then I will focus on to calculate the vertex type frequencies by the vertex type sectors. I call it vertex type sectors. It's called the sectors by Chris Henley, which I had this thought, like basically during when I was in the theta state, have this realization. But then I started to look at the references, and then Michael said there's some work already covering this. So for example, Chris Henley. So I looked at this paper and I found he already covered this part, and he has terms and everything. So then I would just use his term on this, and then so it's a very well explained. Although I feel like his paper, for someone I really understand it, for like very expert of mathematics of quasicrystals, I think they understand this really easily. But for other people, it can be difficult, because he understands it so well. Everything's just so simple. Yeah. So sometimes he does not go into details.
So I have to apologize, because since we have only you today, and I have only rare opportunities to make sure that the rest of our newer group members understand quasicrystal math as well as you do, I can't leave the opportunity to make sure I remind everybody of fundamental things. So when we talk about inflation and deflation, which is a fundamental operation on on a point space, you can equate the inflation and deflations to different shift vector positions of your cut window. So, for example, on that possibility space of the 31 points of the very small section of the Penrose tiling, each of the 12 configurations can be understood as an inflation-deflation, right? Because now your distance between unit lines is bigger than in the point space, because we're leaving 15 points off, right? But that can be, each of those is generated by a different coordinate of your cut window by some shift vector that creates the on-off. So it's your shift vector that does your inflation deflations
Yeah.
Or that's the way you
Well, in
relate?
that case, if you increase the window, then you have to omit certain points because then your unit length is bigger,
Right.
and then that specific vertex that you were focusing on can change it to other vertex types.
Yeah.
That's
And-
why this inflation deflation.
Right. So you control both the scale of your inflation deflation, so you can go up 10 powers of the golden ratio or any number, and then you can create your dynamism. So your scale of the inflation deflation is defined by your thickness of your window, and then your legal position at that inflation or deflation is defined by where you move your cut window. So, sorry.
Okay. So yeah, like I said, I'm not gonna focus on the inflation deflation. If people want to know about it, then I can cover it later, or you can go ahead and read the book, read the paper. So otherwise, I'm gonna continue with the next method because that's my focus. That's what I really prepared. Okay, so okay, yeah, that's cut off a little bit there somehow. So let's ask a question. I want to ask a general question. Like to generate the Penrose tiling, the mother lattice is a Z5 lattice. Everybody knows that, right? So then, what is the shape of the cut window in 3D? Because you have a Z5 lattice. And you project the Z5 lattice to two-dimensional space. And then your vertical space will be 3D, right? So in the 3D, you have a window to select acceptance domain or whatever the cut window to select the point. So what is the shape?
That shape.
No, just tell me the name.
Rhombic triicontahedron.
No. Anybody else? Dugan, you cannot say anything.
Icosydodecahedron.
Icosydodecahedron. Marcelo. Pascal. Cynthiana.
Icosydodecahedron symmetry, yeah.
Okay, so it's a rhombic icosahedron.
Icosahedron, yes. This one.
Right. It's not icosydodecahedron. Rhombic icosahedron. So, which is this shape. And
Which fits inside that, right?
No.
Fits inside here. It's a subspace.
No. It is a. Oh yeah. That's right. So you can see that because.
Okay, let's see if this works.
Notice this window has a planar symmetry, right? So that's why this is for projection.
This is what is drawn.
Yeah. So this is a planar symmetry, fivefold. So it does not have a icosahedron symmetry because it's gonna be for a two-dimensional Penrose tiling. So it's in 2D. And so actually, if we think about the Z5 projected to 3D to the amount tiling, do you guys know what is that window shape?
Yes.
What is it?
The RT.
Rhombic triicontahedron.
Yeah, this is not RT. Oh, this is RT. Sorry, yeah. So if you project the Z6 to R3, this would be the window for the amount tiling. And it is icosahedrally symmetric. And we're going to get a quasicrystal that also icosahedrally symmetric. And vertical spaces, which is the same.
Wait, the first answer, rhombic dodecahedron.
No, that's a rhombic icosahedron.
Yes, rhombic icosahedron.
That's for Penrose tiling.
Yes, and with a different axis. But the RI could be inside of the RT, no?
No, see, think about this. So you can think about there is R3, that's R3 parallel, which is the quasicrystal space, and there is the R3 perpendicular, which is the vertical space. And that's the Z6, and then folded to a three-dimensional quasicrystal, right? So projected three-dimensional quasicrystal, and everything is icosahedron symmetric, vertical space, and then also the quasicrystal space. So how do we relate this to the Penrose tiling? So imagine that 6 axis in Z6. Imagine you just remove one of the axes. And that axis, if you don't remove it, and if you don't remove that axis, and if you project that omitted axis to the 3 dimension, and the axis would be aligned with this 5-fold axis. So this is the omitted axis. Like this is Z5, right? So Z5 projected to the Penrose halide. So that 6th axis is here, right here, in this direction. Oh. And so if you project to Penrose halide, in Penrose halide you can see this. So in Penrose halide you can see that you have these. So this can also be thought as the kind of a corrugated thing. They call some roof. You know, like think about all these rhombohedron are all equal size. So this will be like this direction. This will be like more tilted. This is less tilted. Like it's like a corrugated layer, right? If you think it that way, if you project the omitted axis to Penrose halide to that 2-dimensional space, and that axis is actually also perpendicular to the 5-fold symmetry. So that's a relationship between that. That is why the Penrose, if you project a layer of the amount halide to 2D, it's a Penrose halide.
Right.
So. Okay, so I'm gonna show you. Here is the deal. This is the window, and you can see in the window that this window can be divided into. This is the axis, right? The omitted axis, and the projection actually going to. I mean, how you select the vertices in the vertical space. How you select the vertices. It only selects the vertices that are on the planes, like only the vertices on the planes that are actually, how do I say that?
Yeah, the image of the lattice points into the vertical space is stratified.
Yeah. Okay, good.
The third vertical dimension.
Yeah. Okay, that's a good way of putting it. So yeah, so the vertices that will be selected for the quasicrystal can be stratified. Yeah. So in the window you'll see it will either in this layer or this layer or this layer or this layer, which can be you can see it here. So it can be here in this layer or here or here or here, right? So all the points would all be crowded here because this is your window. Nothing outside of this window would be projected. Okay, so then because of that, so that means if you sum up all the volume of the point that will be selected, they would all be on either this plane or this plane or this plane or this plane. So that's kind of like the volume of all selected points. Although this volume here is really area, right? So these kind of area you can is the sum of all the possible points that will be selected. So then if we calculate the frequency of the vertex, and then we can consider this, as like a whole, and then subdivide, like certain vertex may just only fall in certain area. Just keep that in mind. So that this is why I was thinking of this, and also these people already talked about the Christian Henley's paper, and then also De Bruyn also has the similar picture here. He uses the pentagram method. So it turned out that all the vertex that going to be the sun, the 5-fold, but it's the sun shape, would fall in this little area. If this is a pentagon.
In the top strata?
Yeah. Okay. So then all these, this is got cut off, unfortunately. I think this is a 442. All the points are here. And then all the 4222 are here. This is like the K type, I think. Yeah. And so this would be the star and this is the yeah, I don't remember. The 433 is here, so and you can see here is the D. I think this is a D, which is the one that has no empire, the smallest. So, but it happens very frequently. Like it's a frequency is the highest. So because it's an area, you can see if it is here, then it will be here, 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 here. So I have this map. Unfortunately, I was going to color it so you can compare, because this 5-fold is only this area. And this one, I can color them one area, just didn't have time, and then I don't have glue, I don't have anything, can't find the school glue here. And so, and then this this key type is like these, this little area, this little area, this little area, this little area. So if you sum up all these areas, it will become its frequency, relative frequency, assuming the total is 1. And so here, and this is the 5, and then these are the pretty complicated shapes, like this would be this one. I think it's S3, and then this is S4, would be these 4. So you can see this D shape is like big area, and this J also big area. So you can pass.
Thank you. So Fang, so when we project Z2 to 1D to produce the Fibonacci chain,
yeah,
then we never see any family of more than one point living on a one-dimensional line that's parallel to the cut window. But it seems that this is if you can go back to the previous image or the last image you had, it seems like
they don't overlap either.
No, I didn't say.
Just
No, it doesn't overlap in the example I just said. I said parallel on one parallel line. In other words, if you have your cut window on Z2 and then you draw a line inside of.
But the cut window is just a line, no width.
The cut window can have a thickness.
Yeah. That's the cut window. Cut window is just that line.
Yes. So what I'm saying is, I'm just making a comparison. I'm saying the obvious, which is that if I have a line inside of Z2 that runs inside and parallel to the cut window, no 2 points will rest on that line, right?
Oh, you mean this line?
Yes, that's right. It's
Yeah.
a line inside the cut. So this
Right.
is this is the obvious. But what I'm
Because
saying,
it's totally
yeah.
rational.
So what I'm aware of is that the Z-lattice series quasicrystals are a special case because the projector angle is the body diagonal of the unit cell, right? The projector angle is the body diagonal of the 5 cube or the 6 cube. And so
not exactly, because the projector is a 3-dimensional thing, so it includes that vector, I would say.
Okay.
Yeah.
Well, I can at least say that in the case of projecting a 5 cube to the plane, which is the simplest Penrose tiling that represents the symmetry.
Right. Also, that diagonal direction is inside of the projection space, but it's not just one single vector.
Right, but what I'm trying to draw out is a kind of a question or a statement with you telling me it's wrong or right, which is my statement that I'm leading up to, is that it seems that because of the special case of a fundamental part of the projection hypervector being the body diagonal of the 5 cube, then what happens is on these planes perpendicular to that body diagonal, you actually have families of points living on that 2-dimensional plane. And I'm not sure that there is an analogous case in the more complicated tilings that come from, say, D6, because there, you don't have this special case where the body diagonal is a fundamental component of the hypervector.
Yeah, stratized.
Maybe something to explore, but it seems. I just remember.
Yeah, it's really like a 3D and a 2D thing. So, like if it's a 3 and 3, then we no longer have these things. Like if it's a Z6 to R3, then we don't have this layering.
I guess another way
really
to
more because of it when you project it to Penrose Helen is 2D.
I guess another way to say the question is if you simply repeat this diagram with the exception window that you would use on the D6 tiling to create a three-dimensional quasicrystal, are there two-dimensional planes?
No, but this is a Z5 to 2D. You're talking about D6 to 3D.
Okay, fine. We can take it's fine. We can take D5 to the plane and ask the question: is there an analogous situation?
It would be
where
probably more layers, but I think it would still be.
You'll still have more than one.
What do you
point.
think, Dugan?
The five-dimensional lattice projected to 3 dimensions, to two dimensions, that has the body diagonal, the 1, 1, 1, 1,
Yeah.
1 vector in it, in the projected space.
Yeah.
In the vertical space.
Which is the Z 5-dimensional
Yeah,
lattice.
so that means that you'll have the layering stratification
That's
in
what I'm
the
saying.
vertical space.
Mm-hmm.
That's what I'm saying. It's a special case versus the D5 lattice projected.
No, but
to-
that's the same thing to me. You're just gonna be having more layers because of the points.
So you presume that on a layer you'll have an infinite set of points.
Well, I think even for D6, if you really look at the D6 along the diagonal direction, all the lattice points also gonna be divided into layers instead of
Living on two-dimensional planes.
Yeah. Because it's a rational direction.
D6 is a subset of A6 or Z6. I mean,
Yeah.
Not D6, D5, because I want to take the analogy to this, where this is Z5 to the plane, and I'm saying that because a fundamental aspect of the hypervector is the body diagonal, which is not the case. There's not an analogous concept in the D5
Which is still a diagonal direction for the cube because D5 and Z5 they're related.
Right.
Could be like some decoration. You add some point to certain faces.
Oh.
So basically, this is just a subset of that.
I wonder so do you presume that the acceptance window there would be shapes such as, icosahedron, for example?
Yeah, I don't know for Z6 and D6 they're the same. The window is the same. The window for the Z6 and the window for the D6 are the same. That's what you told me, right?
I would be
So
surprised if it was the same. I wouldn't expect it to be the rhombic icosahedron for the D6.
For the 6, it's different for the 5. But I think
No, it can't be this shape. Because this is like this specific shape has like a two-dimensional symmetry.
I didn't know what you meant when you said the same.
Yeah, it's the same means they both are like this shape.
Oh, a rhombic triacantahedron?
Yeah.
Huh.
6 dimensional lattices, you have the one on the right,
Yeah.
the one with 30.
So even D6, you'd use that a rhombic triacantahedron as your acceptance your cut window shape?
That's what I've been looking at, yeah.
Oh.
But for the 5-dimensional lattice, it's the other ones.
Okay.
Yeah, we're gonna have to check for the D6 projection.
Okay.
So yeah, so
Because
these
the dual of that would be the icosahedron, right? The dual of that shape there. So maybe I would expect for the D6, just a wild guess, not a wild guess, but an educated guess would be that the acceptance window would be the dual of the acceptance window for Z6.
Well, I get a icosahedron as some of the tile types. Project the images and the tile space.
Yeah, okay, so this is what I give you guys there. So you can see this is the golden ratio time. I think this is this one and this one. This one probably is the golden ratio squared times of this. And so the frequencies of vertex types are exactly proportional to the areas. So anyway, so keep this picture in mind. And I tried to make this and I tried to produce it nicer looking, but I wasn't being so successful. But this is like a, what?
That's really interesting.
Can you just restate this? I want to drill into that statement, just make sure
The frequency of the vertex is proportional to the area.
Proportional, so you have 8 vertex frequencies and then...
Yeah, and they're proportional to, for example, if you calculate the frequency of this Q, you just add up these areas. I put this thing here because this
wow.
is the sector or a chamber in this vertical space. That the vertical space, okay, just think about this plus this, and then plus another one of this, and plus another one of this. So 4 of them are the total space that for the vertex. That,
Cool.
you know.
So we can extend that to 3D, where we say the frequency of the
volume.
volumes
Volume.
is
Yes. Yes.
Cool.
Yeah, so you guys didn't get it. The reason I was handing out that, so because I wanted to color this, didn't
Yeah.
have time to do it, but I forgot.
Well, you were sick.
Yeah, so if you really color these, you can see all these red are like there is more red than this color, for example, and then this would be in between. So you color it another color. So yeah, so the area, the frequency really proportional to the area.
Right. Cool.
Yeah.
So it's really deeply a frequency of spatial curvature in the isomorphic form of contraction of volumes in the QSN, for example. It's yeah.
Yeah, I mean, this is kind of like a really like interesting, like, because think about it, in the quasicrystal space, they're all randomly distributed everywhere. But if you look at in the vertex space, they're all concentrated together. All the vertex types of this are all here. They don't go anywhere else. So, but when you look at the quasicrystal space, they're like smeared out everywhere.
Right.
It's like almost, like a hologram, in a way.
Right.
And or like a brain, you have each area that is focused or be responsible for certain things in your body, but you have it everywhere.
Well, when you say smeared out, like how much? Like how can they get very, very far apart?
No, but this vertex type is in Penrose helens everywhere. It's evenly distributed almost, right? And but if you look at in a vertical space, that specific vertex, if you go to the vertical space and look at them.
You mean the lattice, the mother lattice?
No, vertical space.
Oh.
There's the mother lattice is divided into quasicrystal space and the vertical space.
Oh.
Perpendicular space.
Okay, does that relate to the hypervector directions?
Yeah, it's like this is the parallel space. This is the perpendicular space. And so you have a 2D, right? So one dimension goes there, one dimension goes there. They're orthogonal to each other. So for this, we have Z5, which have 5 dimensions. So 2 dimension goes to the Penrose helix. The other 3 dimension is the vertical space. I call it, or pseudo space, or perpendicular space.
But again, just because you said yes, but I want to make sure you know what you were saying yes to. The vertical space or the perpendicular space is essentially or deeply related to the hyperprojector. Yes. Right? Okay, that's what I thought.
That is the projector, if you wanted to call it that way.
So the project that I wanted to maybe kind of test Mike Rios on by commissioning him is to take what you're calling the perpendicular space that we can now call the hypervector values, and to convert that to an algebraic understanding. So to take the algebraic analog or isomorphism of the hyperprojectors that act on E8 to, create the product, as I call it, between the hypervector subspace, because that hypervector now we know is a subalgebra and a sublattice of E8 at the 4-dimensional strata. And so it's self-interactive algebraically. So there's an algebraic self-interaction between the 4D hypervector values and the root vectors. And I think Mike would totally be perfect to try to make that rigorous.
Yeah, this is really interesting. I wanted to definitely dig deeper on this. So just, I needed to show you also what does this mean? What does it mean, like all the vertex of this, for example, can never go outside of this. And we know that in order for the vertex type to be there in the quasicrystal, and all its surroundings, all these tiles has to be inside of the cut window. Because if one of the vertices go out of the cut window, then this vertex type gonna change. So all these neighboring tiles has to fall inside the cut window for it to be that vertex type. And so let's see the mathematical notebook that I made.
Can you close that little window?
Well,
Right there.
okay, so this, I can make it bigger. This mouse is not good.
No.
All right, so the gray window you're looking at is the cut window. Come on.
This is for Z5?
Z5, yeah.
Penrose, yeah.
For Penrose styling. This is the gray window, is the cut window. And then, and then these are all the squares around the vertex. The squares that are going to be projected to the rhombus.
It's the three-dimensional image of the three-dimensional possibility space you were talking about.
Okay. How many squares are there around a vertex?
40,
40?
yeah.
5 shoes. 5 shoes
Okay, so this is no shift. So it's kind of like that, and that the vertex now is at the center. But to have okay, so this is what we understand, and then I want to select a vertex type that is this, which would become the sun. Okay, the sun type. And so I want this to stay inside of the window. And then that vertex, as we said, has to be in one of the strata, right? So that's 5-fold symmetry. So the vertex cannot be here. It can only be this plane or that plane. So if I move this to this plane, let's look at it. If I move it to this plane, definitely that's gonna go out. If I move to this other plane, see still this part is sticking out. So not gonna work. And unless, come on, this mouse is, I moved it to the next plane. See, on the next plane, I can turn on this pentagon. This is the next plane. You can see that vertex is on the plane right now, right? So because it can only be on this plane, can only be on this plane, this plane, this plane, or that plane. So we tried this, and that one is for sure not gonna work. This didn't work. So it can only be on this plane. Right now, there's nothing sticking out.
And then there's that red area.
That red area,
That's where it can move.
right, without getting outside of the window. And so you can see I can move this guy here. And
So that's analogous to kind of an empire window concept, right?
yes, yes. So as soon as it go outside, somewhere is sticking out. You can see there's sticking out. Maybe I can turn on the opacity a little bit so you can see. So it has to stay inside as long as this mouse is not really working very well. At my computer, I can show you like pretty quickly. I can move around this whole red area, and it's always gonna be inside. As soon as you go to the edge, it's going to stick out. So those are the area that this vertex can move, meaning all this S, I think this is called S, all the S vertex type are inside of this little red pentagon. And this little red pentagon, if if we look at it, it is exactly this thing, see? And this big pentagon is this, and this little pentagon is the red one. So that's why this vertex type falls only inside of this area. In the vertical space, again, they're all concentrated in this area.
Yeah.
All these vertex type.
So Fang, let me just insert here for you guys. So this is so Fang has this idea that I like, which is an idea of superposition, where you see the places where she can move this cut window within the boundaries of this empire domain that's represented by her pentagon. There's a finite number. In fact, in this case, there's a very small number of positions where you can move it to get a unique set of points that will be turned on and off, and unique connections in your graph space. All the other interstitial infinity of coordinates are worthless. So when you take that small set, you can imagine cycling through them, either randomly or orderly, and for your physics, you can imagine some action that causes a choice to be made from among some n choices, and that you can imagine mathematically that before the choice is made, you must assume, right, it's in all the states at the same time. Or you could have weights, you could have probability amplitudes for the different ones. You can do various things, but the principle is really beautiful and reminds me of the notion of superposition versus measurement, where when measurement occurs, there's this idea that it shifts from a possibility space of undecidedness to an actualized space of decidedness, or collapse of the wave function, if you use that idea. So I kind of expect that somehow this idea of the statistics of the superposition of these, in other words, the syntax that we speak of in code theory is exactly reduced in the first principles terms to Fang's work on empire windows and the notion of those defining those positions of the movement of the cut window relative to the empire window being your syntactical freedom.
If I understood, so you have the cut window moving the horizontal space, but you can count the frequency looking one in the vertical space.
Frequency?
So what I'm trying to show is, like, for example, this is a vertical space, right? And then you can move. These are full of points in the vertical space, because the vertical space, like, think about all the vertex in the quasicrystal, every single vertex. If you see the component, their vertical component, because they're projection from 5D, right? So then you project to the 2D, and then they also has this vertical component, right? The 3 component. And so if you project all these points, I mean, if you
the vertical is equivalent classes. So
yeah, they're into like a 4 planes basically. This is 1, 2. There is another 2 that is like kind of like a rotation of this, flipping of this. So what I'm trying to say is, in a Penrose heading, these kind of vertex, if you want to have this vertex type in Penrose heading, you have these 4 to 5 tiles has to be in the cut window. If they're not, if one of them or some of them are outside of the window, then you no longer have this vertex type. So then, in the vertical space, I was checking. I have these tiles in the vertical space. They look different, of course, in vertical space. And so I try to move the window around, or just move the point around, right? Shift this point around. I can see that I can move the point here or here or here or here, or any of the place without losing this without changing the vertex type. meaning without one of these squares or rhombus sticking out of the window. So it's always a legal S vertex type, as long as the vertex is within this area. If you go outside of this area, it changes. So then that means if we sum up these areas to be 1, and then the area of this little area, the area of this region would be the frequency, right, of this vertex type. If the total is 1, and this would be a percentage.
That's good. So, and then let us connect this to the QSN to understand that the QSN is the possibility space. That is, it represents the superposition of all of the vibrations, the discrete positions of some cut window of some thickness on E8 or on Elser-Sloan. And when you sum them, you get the point space that is called the QSN. And you can move up from points to tetrahedra, right, or triangles. The concept is still there. And so the QSN obviously is never physical. It's only a possibility space. The only thing physical would be state selections, which are exactly, in some sense, deflation inflations, which are exactly all of the full set of shifts or vibrations of your cut window within the empire window. So it's really a nice, simple concept that is reminiscent of concepts in quantum mechanics, such as, you know, the possibility space of the quantum wave function.
Mm-hmm. Okay. All right. So let's move on then to the 3D. So in the 3D, we have in the true Penrose, like they call it like a regular 3-dimensional Penrose tiling. Amount tiling has this 24 types of vertex types we already have, and then this is their frequency. So in this case, like it's no longer like divided into layers. The vertices is like a volume, like filled with this whole volume, and then the sectors are also like volume. You know, like for example, the one that is, what do you call, 12-foot, or the first one, the most, this one, give you an example. And so this vertex type, and if you look at it, it's sector or chamber, you know, that sector. This is what it looks like, this whole little volume. The size between this and this, I think, is it's a golden ratio square. So then similarly, you can do the other vertex types. You can see that, for example, this vertex type will be concentrated on this little area, but it would be, because it's asymmetric, right? It would be like having quite a few patches. Oh yeah, I can't say like the vertex type all concentrated in one area, concentrated in the areas that has this, that respect the symmetry. For example, in 2D case, in the Penrose case, it's the 5-fold symmetry. Here, it's like icosahedron symmetry. So you have a few areas that would be for that vertex type. And so if you calculate the volume, and the volume would be its frequency. Yeah.
Do we know yet what the average?
8.
Okay, average vertex. Okay. Oh yeah, of course. We just talked about that yesterday.
Yeah. So yeah. So I was going to produce something really nice to demonstrate it, something like this, but the paper model, so we can play. But I didn't have time.
Do you think anyone has ever created a 5-dimensional Penrose, a 4-dimensional Penrose tiling?
No, not that I know of. But
with our software already programmed, isn't it sort of not so difficult for us to do?
Well, it's just like when it's in 4D, there's you can't really see it very well.
Yeah,
you can't visualize
but we can get it into Mathematica, just like we have Elser-Sloan's 4D quasicrystal in Mathematica. We can.
Right, that's why we don't know too much about it, because like think about what is unit cells.
But they published that paper, and I mean we could be the first to do that because nobody's ever projected a Z-series lattice to 4 dimensions in order to create a 4D Amon tiling or 4D Penrose tiling, whatever you want to call it.
There'd be a question about the projection.
It's always the body diagonal. So whether it's Z5, Z6, or the...
You can't say body diagonal. For example, Z6 is not the body diagonal.
Not the body diagonal. The hypervector is a fundamental component. I mean, the body diagonal is a fundamental component of the hypervector.
The body diagonal of what? The 5 cube or 6 cube?
Well, we already know it's a fundamental component of the 5 cube to the Penrose tiling. I'm just suggesting that I remember somebody saying, Julio actually...
No, it's not the Z6 cube body diagonal.
It's not. So that's
right.
just...
I wouldn't give you 5-fold symmetry in that case. Yeah, so it's the 5, still the 5 cube diagonal that is there.
I have a question. So in the case of 3D, we have the Platonic solids and the Archimedean solids, and some of the Archimedean solids have icosahedral symmetry. And so we have the Archimedean solid, the icosahedron, right? So my curiosity is, okay, so the 4D icosahedron is the 600 cell, and the representative polytope of the symmetry of the 600 of the Elser-Sloan quasicrystal is the 600 cell. So there must be a 4-dimensional quasicrystal that is the analog of the Penrose tiling and the 3D Amon tiling. And it would logically be produced from a projection of a Z-series lattice, like Z7. What would be the representative polytope, though, in 4 dimensions? Like, what's the analog of the rhombic triaconsahedron in 4D? Because I know the analog of the icosahedron.
It should still be something like the 600 cell, because if you look at the first layer of this, it could also be the icosahedron in the first layer, because the icosahedron is a part of the rhombohedron, the tetrahedron.
If it's,
so, but then in 600 cell, when you look at the cell, you have to look at the 4-dimensional rhombohedron.
Let's talk about it if it doesn't take more than a week to do it, to project it, and you think it's at least interesting.
No, I don't think it's less than 1 week.
Okay, but meaning we could add it to our discussion list for derivative follow-on problems after this project.
Yeah, we can talk about that.
It's interesting.
Yeah, okay. So, the properties of the sectors, of course, it's easy to deduce. It's non-intersecting, and then it adds up to 1. 1, I mean the whole. No. So it's kind of conserved in that way. Okay, so, and then the next I want to talk about is just a little bit about is the empire and its densities, because it's related to this. They have certain relationships. Jugin's going to talk about more on the details, but I'm just using 1 or 2 slides to talk about. So, so the empire can be calculated by the empire window, we already know. And so using the cut project method, or the valance set using grid method. So Jugin's going to talk about it on Friday. I don't know if how much you can talk about it, because I kind of covered a little bit of this before. And the density of the empire can be decided by the volume of the empire window. So I have this equation, but the density of the empire proportional to the volume of the empire window, but it's not really a linear thing, because there is an empire window. There is this one vertex type, for example, in Penrose, and it has 0 empire, and its volume is not 0. So it could be something like A times V plus or minus something, some equation that we can figure it out. So you can see from here, and so this is comparing these 3 vertex types, right? So apparently, I think this one is the least dense, right? And this one is more dense, and that one is densest. Although, for convenience, I'm picking these 3 because I already have the data there. Otherwise, I would get to that is obviously super different. But okay, so I have a notebook that to just show you. All right, so this is a comparison between those three empire windows. The green window is the cut window. And so I can turn it off. And so the red one is the S, the fivefold. So you can see this is its empire window for this guy. And then K is a window that is actually bigger than that. You can see it has much more volumes here. It has a little bit less volumes there. But in general, the yellow is a little bit bigger than the red.
Is it
this is the yellow.
Is it a stellation of the red?
This is the yellow. This is the red. What?
Is it a partial stellation of the red? Another, I have to see it. So those yellow surfaces are coincident with the surfaces of the red. So it's a stellation where it's just that tetrahedron at the top.
No. This, for example.
The red has holes in it? It looks like it's just a stellation of that one facet.
Okay, so let's. It seems like the red does not have this, but.
Oh yeah.
But let me turn off this red, and then you can see.
Turn off the yellow.
Oh, yellow is like this. Oh, red has more of this on this side, and then turn off the yellow. The yellow is this.
See, it looks like.
Is that representing three areas?
Okay, so the only difference is this versus that.
But you can compute the volume with mathematics.
We can, we can. I'm just because I didn't have in.
Well, actually, it looks like the yellow one is right there on your left is a different piece because I don't see a red. I mean.
Which this side.
No, that's new. But that right there is that coincidence with the red?
I think so. Yeah. Okay. Let's see this right. See this edge.
Yeah.
Okay. If I turn off the yellow. See, it has it there.
Oh. So it looks like the only thing added is the stellation.
This versus that. Yeah.
Oh, that one on the right is not there on the yellow?
Yeah.
I mean on the... No, the one on the right is there in both cases.
No, the yellow is not there.
No, the yellow's not there. Oh.
See, the yellow has it has a square. But the red is a pentagon, I think. Oh, okay, no. Yeah, the red. Anyway.
Okay.
Yeah, so they're pretty similar. The densities are pretty similar. This one and that one. And this one's bigger tiles than that one. So if you shrink this a little bit, these two are actually similar. But and this is definitely sparse, so we can see.
It's quite clear that the one on the right has a higher density than the one at the left. The density of the green parts compared to the white part.
It's not because these tiles are a little bit bigger than these tiles, so it's not skewed correctly.
Yes, it's clear with
it's clear to me. It's clear to me that the one on the right has a higher density than the one.
No. Clear. I'm saying this has a bigger tiles. So if I shrink it a little bit.
Oh.
If I make them the same. Density. If I make the same tile.
No, it's the relative density of the green compared to the white.
The black lines should be the same in both, right, Fang? Like this is the same scale.
Let me see if it's the same scale.
It might not be the same scale if it comes in.
Yeah, if it's not the same, it's still similar though.
I mean, because we know from the Laura Dean Effinger paper that some empires are denser than others by...
I don't know why this is small, but...
Right, Fang?
Huh?
We know from the Laura Dean Effinger paper that some tiles have some empires have a significantly different density.
Yeah, that's why I didn't choose the good one. I mean, this is less dense than that, but I should have chosen one that is like super different, you know. But this is definitely the least dense. Yes. So that's why, you know, in this here, between yellow and the red, it's difficult to. Unless we calculated it, otherwise it's difficult to see. This is definitely more than that. But to me, I mean, if we calculate, it should. But let's see the other one. This one is definitely less than the red, for example. I mean, it's less, but yeah, I just didn't pick the good example.
It looks like the two on the left might have the same density or almost the same.
This is definitely less.
No, because look, each one of those is a cluster. Many of those are a cluster of 3 tiles close together, and every one on the left is an individual.
Yeah, but if you count the number of green tiles, this is definitely less. So, but anyway, this is like I got this slides basically 20 minutes before the talk, so I should have picked another one that will show. I mean, it makes sense, right? If you have a bigger empire window, you capture more tiles. So it doesn't need to be proof on that, but it's just like how.
Actually, I just counted, and they're about the same. Yeah.
I don't think so. So how many of these?
About 60 thick tiles in each, and then the one on the right also has the bonus of the thin tiles.
So 6, yeah.
And then you can easily count
Here
that.
there's like
10 times 5 plus another 10.
So this is already 50, right?
Yeah, it's 50. And then
it's a 50, and then this is
and then
kind
you got
of
5
another.
5 times 5 is 25. So that's.
Yeah, so this is over 100, I think. These are the over 100. That's like a little bit less than 100. So anyway, what I wanted to say is the frequency of the vertex type, like it's actually a little bit inversely proportional to the size of the vertex type. If the size of the vertex type is big, then it has, I don't know if that makes sense. It's just like if the size is big and in the vertical space it has less space to move, right? So it has the frequency is actually low. And if you see where's the board? If you see these, this one, most of the complicated like vertex types are like crowded in these small areas. And this is actually very simple, but it has big areas. But this is not as simple. It still has a big area. So I can't conclude that. I'm just saying, like, it seems like the frequency and the density of the empire seems to be a little bit inversely proportional to each other. Don't quote me like a linear proportion. I'm just saying, like, it seems like the vertex type that has a higher frequency have lower empire density. And the highest frequency of vertex is the D type, which has 0 empire. And the lowest frequency would be...
Oh, yeah, Fang, you can see it on your chart on the right, just on the little diagram on the bottom right.
Yeah, so the lowest frequency is this one, or this one.
Right, the 7, the 7 degree vertex is lowest.
And then it's the empire of either this one or this one, I think, are like the densest.
Yeah.
If I can, it's just I didn't pull out, but these two I remember has like a really dense empires.
I bet you it has a nice kind of equation or something, like nice looking, whatever it is, you know.
Yes,
if it's not linear. It's
some kind of relationship, like inversely proportional. Okay, so like I was saying, the whole purpose of working on the vertex types, the frequency and the empires, is to for the efficiency proof of QSA, and we have discussed that the efficiency should be proportional to the average valence rank, and it's inversely proportional to the number of lanes. And so, or I can, make it simplified like this using the less letters. But how do we even define the valence rank in QSN? What points should we include and what connections should we include? Because Ray calculated, for example, the valence rank, and he actually excluded the vertex that has only 1 tetrahedron or 2 tetrahedron connected to it, and then got a number. So anyway, so maybe really we should calculate the dual of the fig, which is a space-filling quasicrystal. The dual means the real dual, like because any great space you have a space filling QC. I was working on this a little bit, but I didn't continue. I worked it a long time ago, and recently I worked a little bit more. So because it has too many cell types, how do we kind of categorize these cell types? It's a little bit too complicated. So, but all we need is the edges, and most 2 edges. So we could use just the edges for vertex types to categorize vertex types. We need to compare with the average valence rank with a similar quasicrystal, like the amantaline, to compare their efficiency, if we believe the efficiency is defined by this. So this is why I have this table. I worked on this table a little bit. So obviously for Fibonacci chain, modulus is Z2, 2 types of vertex types, long or long short, or you can say 3 if you include the mirror symmetry one, long short, short long. And then the average valence rank is 2. That's obvious. Every vertex has a valence number 2. The number of edges is 2. In Penrose tiling, modulus is Z5, and then it has 8 types of vertex types. The average valence rank is 4, and it has only 1 edge length there. And so then in amount tiling, its modulus is Z6, and then 24 vertex types. The average valence rank is 8, so I calculate this out using other people's number, for each vertex type and the coordination number and its frequency. And it also has only 1 edge length. So for the 36 vertex type QC, it's projected from D6. It has 36 vertex types, one of them, because you can project D6, you can have different quasicrystals. There is a specific one that has 36 vertex types. And unfortunately, I calculated the average valence rank to be an irrational number, although it's golden ratio related, but
it's a weird looking number.
Yeah, but anyone can feel free to verify it.
Or but can it be reduced?
Reduce it. How? This is really simple. This is directly the integer, at least.
Expressed more compactly.
How more? It can be more compact than that. It's just an integer plus.
That's what I'm asking. I didn't.
No, this is. I mean, how do you simplify something like this?
Well, you have a number of symbols there, 1005, 454, meaning there's enough symbols there. So in compactification, you just...
No, this is not 1005, this is a 1 number.
Well, it's not.
This is 1005, that's 1 number.
I acknowledge that, but...
we can make a symbol for 1005.
Okay.
Let's call this...
It comes from the idea that a number like 700,458,323 contains more information and generally requires more symbolism than expressing the number 1. Like, to give you an extreme example, like there's some kind of theorem that people better in math than me could come up to say that big numbers contain more information than smaller numbers. Like they're set theoretic combinatorics.
So what do you want to do? You wanted to make this 5 times 201 and things like that?
I don't know. I'm not sure it can be reduced, but what I'm saying is, we've done a lot of work over the 9 years.
Yeah, unless you want to express this with smaller number, but then you're going to have a long equation. So.
Then you'll make it longer on the other side. Okay, but anyway, I'm happy it has square root of 5 in it.
Okay, so the interesting thing in this exploration is the Arcelon quasicrystal, because I spent quite a few days on this modulus Z8, and I haven't figured out an analytical way of calculating the average valence rank, but I was trying to calculate the bigger and the bigger patch of the Arcelon quasicrystal by using 10,000, 20,000, 30,000, 40,000, 50,000 points. But then the average valence rank for 10,000, I got a 57.7. For 20,000, I got a 56.5. You can see oscillated from 57 over, under, over, under, over, which is really interesting. So that means the average is 57. So for 10,000 points, the average valence rank is this number. For 20, it's this number. For 30, it's this. So you can see it's just like always above or below 57.
Wow.
So we can kind of guess it could be just around 57.
It could be 57.
Yeah. So which is really interesting.
That's totally interesting.
And then I start conjecture. Oh, so 57 is a dimension for the Yate algebra. Maybe 8, 8 is the same number for Z6, but nobody can confirm that because seems like that 57 is defined by the E lattices. There is no clear kind of way of calculating for the Z type of lattices or algebra. Okay, so then for QSN, you can say its mother lattice is E8 or else quasicrystal, but that's a quasi-lattice. It has many vertex types, and so recalculated this number if you ignore the 1 or 2 tetrahedron vertices. And so this number is not very high. Compared with the Mount Tally, it is higher, but we're ignoring the low degree vertices.
So hold on, E8, Elser Sloan, QC. I'm sorry, what is the difference between, so that's the QSN. So this 12.34 is the average, let's see, you have the QSN on the left, and then the mother lattice is the Elser Sloan. Okay, so you're projecting Elser Sloan to 3D.
No, just I have to say who is its mother lattice. And you can see if it's a lattice, really it's from EH, but you can also say it's from Elser Sloan quasicrystal, but it's no longer a lattice.
Okay, and what did Ray do? What did he include?
Recalculate the average valence rank for QSN.
Did he include tetrahedral vertices?
Yeah, all the tetrahedral vertices.
So you're mixing the tetrahedral vertices with...
No, the tetrahedral vertices is the vertices of the QSN.
Well, they're edge crossing points, and they're
I think he also included the edge crossings.
No, I didn't.
No, you didn't?
No.
Okay.
So that I have a method to compute it, but this method should be reviewed and worked more. So I can have this result. I can
see that if he included the edge crossing point, this number would be lower. And also he ignored the lower degree vertices. If the vertex only has one tetrahedron connected, like basically degree 3 or degree 6, he ignored them.
Oh,
yes,
that's
because
what
we have a network of tetrahedrons, so this
that's
is
what
different.
I want. Like in other words, if you have a 20 group, I would count the vertex at the center, but I wouldn't count all the other ones. If
well, no, we want the average valence rank. We have to
is this
include
one of the
all
20
vertices.
problems?
What this
this one we're talking about right here at the bottom.
No.
The QSN.
Compute the valence of the QSN. It's not in the 20 problem.
Average valence rank. I mean, it is here. This is the problem for the efficiency.
I don't
remember. But Cleve, for the efficiency proof, we already agree we have to calculate
the
valence
25.
rank.
I'm just asking a different question. I'm saying, without me stopping to read that whole list, is the average valence rank of the QSN one of our 20 or no?
Definitely not one of the 20, but it
could be added in the future.
Yeah, could be added, but I think I included it in the efficiency proof.
Which
so
is
the
25th.
Yeah, it's important to get on the same page about it because I really want to know an answer to a question relating to average valence rank, but there isn't a wrong and a right. There are definitions of what valences you want to count, and I have a... It makes no sense to me if you ignore the low valence and then just say, oh yeah, QSN has high valence rank because we're ignoring the lower As
valence.
I always say, I strongly encourage us to always compartmentalize our thinking into the space-filling regimes of the QSN and the
which is this one,
non-space filling
which
regimes.
is this one, we have it.
True.
If this is, the space filling.
True. Okay.
So I believe we have to work a little more on this, but now we have all the data, but we don't have defined clearly what is the valence of what. So
Yeah.
I have
there's
some
more needed
proposition,
to
but
be-
I have stopped to work on this to work on other problem.
Yeah, I mean the valence rank as a whole theme that is definitely an under.
And really depends, yes, if we are looking at the tetrahedrons, the 20 group centers, the edge crossing points, we may get different value, and for me, we have to compute everything, every combination,
We might want to
choose what is the best.
A few good combinations. Fang, can you go back one slide, please? So,
By default.
Cynthiana Dugan, Marcelo, Pascal Ray, how much do you agree with or understand the idea of the efficiency proof? Do you understand or agree or disagree with the idea that average valence rank?
I agree.
Okay. Anybody else not sure or agree, disagree?
Lower balance means more efficient.
No, higher valence means more efficient. Yeah, I mean, generally in network theory, where you're worried about. Yeah. Okay, and then do you guys understand? Okay, and do you guys? What does everybody think about the idea of understanding, relating it to the number of symbols, where the irreducible symbol is a one-dimensional object, lengths.
Yes.
And so this is a big deal for me, for Fang to realize that she thinks that the valence rank is inversely proportional to the number of lengths, and I now have a deeper understanding of that actually from the beginning of your presentation, where you helped me to understand that the vertex frequency relates to the geometric, the dimensional volumes and areas, and that's a really good understanding for me at least. And it makes me wonder how that's connected to this understanding of a possible inverse proportionality. Because in other words, then you can eliminate lengths or you can eliminate average valence rank, and you could focus after demonstrating the inverse proportionality here, then you focus your proof on either the average valence rank or the number of lengths in a network. And so with we know that 2 is a special number, right? Because there is no quasicrystal that has an average valence rank of 1, right? So 2 is your kind of next minimal number up. And we know that QSN has that. Anyway, I just want to say before you go on, and we can take a bathroom break if you want soon, but
I'm almost done.
Okay, then almost done. So I just want to keep selling everybody here on the importance next year of articulating what efficiency is and then figuring out how to mathematically prove it with a formal mathematical proof once we've defined efficiency. And I've been talking lately a little bit with Stephen Wolfram, and I can just tell you, him and a lot of other people would be extremely surprised and interested if a little group that no one's ever heard of, QGR, figures out a proof in network theory of, with the restrictions of our definitions, of the maximally efficient network, right? And in Stephen's case, he has this lifetime passion that besides Wolfram language and those things that he's passionate about, and he's got like 800 employees at Wolfram, and they're all coders and those type of people. It's a big company. But he told me this last week. He said, if it wasn't for this company, like I would be working on the stuff that you're working on. And so what Stephen Wolfram believes is that secretly there's an undiscovered Planck scale fabric of reality that behaves as a graph code where it's reducible to a trivalent graph, right? And he wants to try to search by brute force through the universe of all possible trivalent graphs, right, to find the trivalent graph which is most suitable for simulating realistic physics. So I reject that idea. I reject it because I think it's smarter to instead start the way we're starting, which is try to first find a theorem or a concept that allows one to define the efficiency of a graph or a graph drawing and restrict and control your definitions. And this kind of path so we suspect, me and Fang, maybe Ray, some of us suspect that because of this extraordinary valence rank of degree 60 in the QSN, and because of some understandings that at least Fang and I have of sphere kissing problems, we have this vague picture of maybe why, or the path of how you prove with geometric mathematics why in a flat space you cannot get a 2-letter code, or a code that can be constructed with only 2-letter chains that has a valence rank higher than the QSN in 3D or higher than the Elser-Sloan in 4D. And if that's true, and it could lead to a proof, I think it would be applicable to a wide range of science and computer network theory and whatnot. But Stephen would be one of the people like us who believe that, look, nature is worried about efficiency. That's what Noether's second theorem is about, because the special case of Noether's theorem of the principle of least action is just one example of nature's attempt to find the simplest expression in terms of actions. And so if nature is a graph theoretic kind of structure playing out, then it should be the maximally connected graph, or the graph with the least number of lengths, or some kind of definition that you could reduce. And then you try to find that and then prove why it's that, instead of doing a brute force search because we can reduce the QSN to a trivalent graph. Right? It's reducible to a trivalent graph. So that's why I'm so passionate about this efficiency proof next year, in the first half of next year.
Okay, if I can add some words, yes, I totally agree with the basic principle, and I have the faith like you and like Stefan that the universe is made of a trivalent graph, which is described by set theory, and this is the simplest possible mathematics model. And also I agree with you that the good approach is it's not the brute force, but it's a smart approach by looking what is the most beautiful mathematical object which encodes physics, and clearly this is E8. So the beginning is from E8, and there is no doubt on this. Right. Then in my own exploration, I was from E8 to the beautiful crystals, the 24 cell, F4, D4, which are very important. But in the same time, you have gone from E8 to the E8 Elser-Sloan quasicrystal, introducing phi and the 2 edges, 2 lengths. And in fact, by combining the E8, the 2 lengths, we will have this trivalent graph, topologically defined, but which is also scale invariant. And the scale invariance of this topological graph is the last element we need to make a quantum mechanical theory.
Yeah. So listen, this idea of forcing our tetrahedra to be non-deformable forces the explosion by a factor of at least 5 of these degree 12 vertices. Like you'd have either degree 30, let's say you have degree 30 or degree 12 vertices in the projection of E8 to 3D, or the projection of Elser-Sloan to 3D. And in that case, you can't construct the 36 vertex type with some quantity of Fibonacci chains. So you have a lot more fundamental lengths in your fundamental one-dimensional chains. There's exactly 7, right, fundamental lengths where the root vectors of E8 get contracted to 0, and then 7 other lengths. And so in other words, think of it like this: by allowing more degrees of freedom in your letters of spatial curvature as contractions of one-dimensional length of root vectors from E8, now you're painting a picture with 7 + 1 expressions of curvature. If you force yourself to paint a picture of curvature with only 2 fundamental expressions of curvature, what happens is, to express the geometric frustration, where you don't allow the system to express these degrees of spatial curvature in more than 2 edge lengths, what happens is you pop out these tetrahedral edges. They refuse, in some sense, in the compound quasicrystal, they refuse to express geometric frustration or spatial curvature by contraction. So now you have to push more of your expression of spatial curvature into a different expression of the information. And that different expression takes the form of higher vertex, a higher average valence rank, right? And in some sense, a denser, a denser network. So if you take this 36 vertex type and you'd ask Fang or Dugan, well, what is the highest valence rank there? What's the highest valence rank in the 36?
12.
12, right? Or it's 12 or 30. I mean, if you placed a centroid at the middle of the highest.
No, not 12.
Okay, so
it's 24, 40 or something.
I think it's okay, but whatever it is, it's a lot lower than 60, right? So you can at least speculate that when you calculate the average, right, the average valence rank, you might get a higher number in the QSN, but you have to cast out the tetrahedral vertices in some sense, and you're looking at the degree 60. Because something like Fang's compound quasicrystal, right, it's got all these degree 60 vertices everywhere, and then it's got some degree 16 or some 16 tetrahedron ones, and right, so you have 16, you have a 4 tetrahedra, right, which is 12. So anyway, you have all these high numbers, and then you get an average of those fundamental vertex types that's just really high compared to the space filling one. So anyway, that's why I think this object, the QSN, is really special. And then code theoretically, if your code allows you to rotate right or left, then every time you see a degree 60, you have a mirror copy of a very different geometric object, but sort of sharing the same centroid. It's just a different object. So somehow you got to count that. And then whenever you find out what your code is, if your code allows combinatorics to alternate of right-left in some legal state of your rules, now you've got that right-left acting multiplicatively with your ability to express information. And you may very well explode the combinatorics even greater than what you get in the Elser-Sloan, which has a degree of 57 average. And then you could argue, well, that's why nature uses the QSN, right? Because it's simply nature for some reason. Again, I call it the principle of efficient language. Nature is just worried about efficiency for binary actions. Why? I don't know. What's the purpose of nature in the first place? So
yeah, well, but this is in 4D though. You have one more dimension.
You have more dimensions. So you got to figure out how to deal with that,
Yeah, well, I'm just saying one more dimension allow you to have more connections.
Mm-hmm.
Okay, so from these average valence rank, we just conjecture it could be 2 to the n's. Well, that's why you mentioned about if we could do a 4-dimensional one, maybe it's 2 to the 4s. So yeah, that's something that we can think about later. And also, this average valence rank may be able to, the sphere packing could be able to explain the average valence rank. I have a good feeling about it, but I haven't looked into it yet. And so this is just showing a diagram that I got for when I calculate the vertex average valence rank in Elster quasicrystal. You can see I have blue, red, green. So, and I think this is a 57, 56, 57 around here. And this is something, this is a big number that is maybe 43. I don't know.
But if that one's 57, how would that one be 43? That's bigger.
Yeah, but it's only like, for some they are bigger, but for some this is small. But if you actually put an envelope around this whole thing, it will center around the 57. Yeah. But I'm just pointing out these interesting few peaks. You know, these like when I increase the number of points, for example, the frequency of these vertex types never change. So only some of them change a little bit.
What does that mean? Frequency change?
Like if you count the vertex types of this QC, and you have certain vertex types and the frequencies, and if you make it larger, and in this layer, in this shell, only like 2 or 3 vertex types in this shell. If you get another shell, there is only like sometimes even just one vertex type in this whole shell.
Okay.
So that's what I mean.
Okay.
Yeah.
Fang, do you have any crazy idea on conjecturing other than what you already said? Like, why 57 might, if it is, be the average frequency of the Elser-Sloan quasicrystal? It's easy to say what
average rank, not valence rank, not frequency.
Oh yeah, I'm sorry. I meant to say, thank you. I meant to say the average valence rank. Like if it is 57, let's pretend that it is. Now, if it is, obviously it's easy to speculate. Well, maybe it has something to do with the stuff we were talking with Mike Rios about. But okay. But how? Like exactly?
Yeah. It would be very interesting to figure that out. But no, I haven't actually continued thinking about. But that's very interesting.
I suggest that we calculate up to, go to 10,000 points. You went
we already have 40,000.
Okay, so I suggest that we just convince ourselves that it's really wobbling around, approaching an average of 57. And once we're at least like 98% convinced of that, then I think it becomes a candidate as a phase 2 set of problems, because it now will be obviously, because the best answer that sounds interesting is this stuff that we started talking about with Mike Rios about how 57 so deeply related to E8.
Yeah, we could do bigger patches, just like the computer is a little bit crazy about dealing with so much data. But we could do it layers and get some other layers.
Oh, right.
Patch them together.
Oh, yeah.
Yeah. Okay, so this is my summary, the last view graph summary, and the next things to do. So the vertical space or pseudo space is very important. That's my conclusion from this talk, because it seems like different areas are responsible to the frequencies or empire densities of the vertex types. Like I said, the volumes could correspond to the frequencies, and then the volume can also correspond to the densities of the vertex types. Kind of like the brain, like it's a small little window there, but each area is responsible for certain functions. So can be thought as the consciousness space. That's just my crazy thought, that has separate chambers for different kind of responsibilities. Okay, so and the next thing to do is to get more clarity on the average valence rank, which include the 57 thing, or included the Y2, 4, 6 and all that. And then also the efficiency proof of QSN.
If I could add to your bullet point number 1, I was, for those who haven't heard, so I was...
Hold on. I also said the operation here. So this is operation means action also. So it further confirms like the actions that I talked with Marcelo, like if we could really like consider about this operation or this action function in this vertical space, and then that's kind of like I don't know if it's good to call it the implicate or something. So the actions is in the vertical space in the operation window, like it does the operation. And then in the quasicrystal space, that's more of the explicit or the reality thing. So we have talked about that. And of course, like to create the face-on dynamics and all that pattern, and all need the kind of changes here, in the vertical space. So, so it's like this vertex. For example, a flip of a flip does not change its vertex type. It's just a flip, right? But if I change the vertex type, then that's kind of like the interaction between these kind of different chambers or different sectors.
Yeah.
So if we just like focus instead of just purely on the quasicrystal space, in the quasicrystal space, if we actually start thinking of the vertical space, because we have a better idea, better image of what it is like, maybe that can help us.
I 100% agree.
In the continuum picture, you have the geometric connections that, so understand, you can split in the horizontal and vertical connection.
Yeah.
Which is understood to be about dynamics. There is the connection, and the connection is, you have this split, and in the vertical space you have it's an equivalence class, so you have a group of symmetries that connect each. You can move one point in the vertical space by a group transformation. So it seems very related to this, how we encode information in the vertical space.
Yeah.
Mm.
But you have the dynamics in the...
Yeah.
Good.
Yeah, I mean the area, the volume, the area, and even the location in the vertical space, it could be a parameter.
Right.
When we try to describe matter, energy, and all that, so
yeah.
be all candidates.
I want to connect something that I think is everybody will be interested in, and it's really an elaboration on your bullet point number 1, and also what you verbally said about number 1, where I agree with you, and with what Marcelo said. But if I could use the whiteboard to explain. So Garrett Lisi caught my attention when with a statement he made, where he said, it's sort of like physics is E8 gone wobbly, right? So imagine E8 like a bowl of 8-dimensional jello, and Garrett sees these vibrations in the jello. So the jello has gone wobbly, and physics is the expression of that. Stephen Hawking said, I really want to know not a lot more about the equations of nature or the gauge symmetry equations. I deeply want to know what is it that breathes fire into the equations. In other words, he's asking, what is it that animates these equations, right? And then the third quote that was inspiring was by Cole Fury at Cambridge. Cole Fury said, she thinks that fundamental physics can be deeply understood conceptually as the E8 Lie algebra acting upon itself, right? The algebra acting, self-interacting with itself. So these are just different, kind of allegories, concepts. So then once Cole Fury said that, I realized something. At first, in the first period of us, me and Fang, doing this, I always essentially thought of the hypervector that acts upon the E8 lattice as kind of being something that's added in, as opposed to something that's deeply implied by the E8 lattice. In other words, if you take this square and you to arbitrarily draw an angle through it, okay, and then you take these 2 points, is it fair to say that these 2 points are deeply implied by the square? No. Is it fair to say that these 2 points and that angle is deeply implied by the square? Yes. It's a different thing. You can argue, you can say whatever you want, but there's a difference between the body diagonal. There's a difference between the centroid of a regular object and some arbitrarily chosen point. So by that kind of way of thinking, I used to believe, because of my ignorance, that these beautiful hypervectors that we used to operate on E8 or on the 5-cube lattice to produce the Penrose tiling were somehow just chosen because they happen to be the hypervectors that bring you to a regular symmetry in the projective space, right? So the hypervector which acts upon a slice of the E8 lattice brings you to H4 symmetry in 4 dimensions when you create the Elser-Sloan. But then I learned that actually, I learned this from Fang, but actually the hypervector that transforms a slice of the root vectors as expressed as a slice of the E8 lattice. So this hypervector acts upon the E8 root vectors. This actually is a subspace, not an added in chosen hypervector because it does what it does. If you go down in the E8, right, the E8 lattice embeds E7, right? It embeds E6 and so on. So it has these sublattices. And then I thought about the fact that the E8 lattice encodes the E8 Lie algebra, right? So that's not a lattice, that's an algebra. And so there's a 4-dimensional subspace of the E8 lattice, a fundamental 4-dimensional subspace, such that if you had a number of copies of that subspace and you could rotate them into higher dimensions, you could generate the E8 lattice with this 4-dimensional subspace. The hypervector which acts upon the E8 lattice is derived exactly from a 4-dimensional subspace. So now let's leave the realm of geometry altogether, and let us take the algebraic equivalent of the hypervector, which comes from the 4-dimensional subspace of the lattice, and we're just going to call this, hypervector algebra. Okay? And that's an object, an operator, a transformer. And then we're going to take the other object, which is also an algebra, which is just the E8 Lie algebra. And that's a second object. And then from this simple realization, it hit me that it's much richer than the E8 root vector algebra acting upon itself. It's the physics that we're looking at is the algebra, a sub-algebra of the E8 Lie algebra acting upon the root vector algebra of E8. And so this self-interaction is what we here are looking to isolate and derive, right, and demonstrate. And it's distinctly non-geometric, right? It has a geometric analog in the cut plus projection formalism that mostly me and Fang have thought about for 9 years. And that got us here to a certain point. But the algebra is going to get us beyond that point. And well, of course, that will be something I can have absolutely no contribution to. But I can contribute this simplification of a vision, of an idea. And then people like Pascal or Ray or Mike Rios, like people who love algebra and can simply understand me and Fang's more visual, intuitive cut plus projection understanding of possibility spaces, cut windows, empire windows, vibration, superposition of cut windows relative to empire windows, and all of these important things that get us to that understanding, that can all be converted. So now, as I explained with the simple case of the Penrose tiling, you have only 12 in the smallest sample of the Penrose tiling that maintains H2 symmetry. You have only 12 possibilities of how the hypervector algebra acts upon the algebra analogous or isomorphic to the Z5 lattice, right? So we want to be restrictive, in other words. I don't want every single algebraic action that is possible between the hypervector algebra and the E8 Lie algebra. I want the subset of those solutions, right, which are allowed by how you define your restrictions, which is you have to define your cut window, its thickness, and its vectorial freedom of its shift vector code, if you will, its shift vector degrees of freedom, and the shape of the window, right? So the shape, the size, and the vectorial allowed dynamics of how it can move from operation to operation. And that's the subset of these solutions that defines a statistical possibility space, where within this subset of solutions, you then find out questions like, well, are some solutions higher probability than other solutions, and why? Like, why algebraically and geometrically would one solution have a higher probability amplitude? So, Marcelo?
Just a comment that, for me, a clear element of this subset, subalgebra, is you need to remove the crystallographic restriction from the Lie algebra. Because all the Lie algebra theory, you have the crystallographic restriction. So, the point group symmetry of the E8 lattice is the Weyl group of E8. So when you look to this subalgebra, you should remove this restriction and work with more general Coxeter groups. I think it's a base element of this extension to look for this subalgebra, where now you try to understand this Lie algebra theory without the crystallographic restriction, which is foundational when you look on the structure of Lie algebra.
I don't fully understand it, but it sounds interesting. Fang, do you understand that? This crystallographic restriction idea by removing it by going to a Coxeter representation.
Yes, which are H2, H3, and H4.
Yeah, but that's different than what I'm saying. I'm saying you have to take the crystallographic and the analog of the crystallographic lattice, which is the E8 Lie algebra in its entirety, and then you have to take this completely separate algebraic regime, which is your projection operator regime, which acts as a transformer of this.
So you put the H4 there, in fact, yes.
The H4 is the H4 the H4 is the product. In other words, this is a coefficient, this is a coefficient. You don't get I don't know that you get H4 until you get the product of the two coefficients. This is the E8 Lie algebra. Okay, this is the hypervector algebra. In other words, our formalism uses a hypervector, not an algebra, geometric operator, and a geometric slice of a 8-dimensional lattice, the E8 lattice. So we transform the lattice slice with the hypervector to get the H4 or H3 quasicrystal, right? So that's what we do. But you can leave the regime of geometry, and you can go to the regime, you replace this with the hypervector algebra, and you replace this with the E8 Lie lattice. I mean the E8 Lie algebra, not the lattice. So the E8 Lie algebra, and then you have object 1 and 2. This transforms this, and in some sense this transforms this. So you may look at them in some sense as coefficients, which together produce a product, which is either the H4 or the H3 quasicrystal, or you take a slice of this and you compound it to create the QSN, which is also a product because it encodes this. And so that's not a crystallographic restriction. It is a transformation of the crystallographic analog algebra of a hypervector algebra, which the hypervector algebra is a derivative algebra or a subalgebra of the E8 lattice, right? It's not just an added algebra from some outside source because we like it because it brings us to H4 and H3 symmetry. It is specifically derived from the lower dimensional root vectors of a lower dimensional sublattice of E8?
You have the E8 lattice, you can look for the related algebra, the E8 algebra, and you have these two perpendicular space.
Which comes from the four-dimensional subspace of the E8 lattice. So therefore it's a lower, therefore it's a subalgebra already built into the E8 the higher dimensional E8 Lie algebra.
Yes, and to generate the H4 Quasicrystal, they are irrational. So they are. You should look for this. The relate, like the E8 algebra relate to E8 lattice. What is the algebra relate with H4 lattice? Because there are two in perpendicular space. There are two H4.
Well, to me, the algebra associated with the quasicrystal of the four-dimensional Elster-Sloan is a subspace of the quaternions, which is the icosions, and this has already been studied. But the question you should be asking, in my opinion, is exactly what is the algebraic analog of the subspace down here in 4D where the hypervector geometry lives. In other words, you lift a hypervector set right out of a sublattice of E8, then you operate it on the E8 root vector space in 8 dimensions. So in some sense, the full stack, the full algebraic and geometric stack of the 8-dimensional down to the lower dimensional sublattices and subalgebras, the whole structure self-interacts with itself from the 8D to the 4D space. And the product of this self-interaction is an H4 or H3 or QSN, depending on what you want to study, product of this interaction. And what I'm saying is we already understand now the geometric side of this. And we understand it pretty well. What we don't understand yet is the algebraic isomorphism or analog. And that's what I want to do in the first part of 2018. And I was thinking Mike Rios could be on that team. Like, it doesn't have to be just him, but he could be on that team because he's so interested, because he knows Cole Fury, who inspired me to think about this in the first place. And he loves what we're doing. He loves E8, right? And he likes the idea of, I've explained this to him already, he likes the idea, he agrees with the idea of a subalgebra acting upon a higher dimensional algebra in which the subalgebra is embedded. So.
Yeah, so before we finish, I wanted to kind of emphasize on this correlation.
It's cookie.
If this is the parallel space and this is the perpendicular space, this is what it looks like. Like in the perpendicular space, for example, these are the purple vertex types. It corresponds to one vertex type. And they spread it out, in the parallel space, which is the Quasicrystal space. And so you can see the orange one is because it's a bigger area, it has more there. And this one is small, so it has only a few, this cyan one. So just like, the reason I keep repeating this is so you actually, remember this by,
Can you
printing this picture in your brain.
Some of the terms maybe confuse me. Can you just try one more time?
For example, this one is purple represents one vertex type.
Okay.
Certain vertex type. And in the perpendicular space, this is how it is located all together in this area. And if you look at it, this vertex in the Quasicrystal space, it's
rearranged, spread out.
It's scattered, spread out. Yeah, it's just like evenly spread it out. And so, and then if it occupy a bigger area in the perpendicular space, then you have more density there, but it's always spread it out. But if you look at the perpendicular space, they're all just concentrated. This vertex type never mix with that one. They don't mix with each other at all.
So I asked this when you were doing the presentation. So because your cut window is always finite, the only spreading out that occurs is relative.
Quasicrystal is infinite. The
Okay.
cut
Yeah.
the cut window is finite, but in the parallel space is infinite.
Okay, I still gotta say what I'm saying because that didn't help. If I use the example of the Z2 projected to the line, it's probably a way to tell you
the line
what.
is infinite, right?
Well, you gotta let me say it, and then you deal with my.
Yeah.
So when I have a cut window of some thickness on Z2, okay.
Yeah.
What happens is my points can be very separated, right? Perpendicular to the thickness of my cut window. And so, yes, it gets rearranged on the one-dimensional subspace that it's projected to, but it doesn't get rearranged in the other direction very
In
far.
the vertical space, right, they're all concentrated there.
Right. So it's not like the analogy of a hologram where it gets fully distributed, represented everywhere. It gets rearranged sort of in the projection space in a limited region, a limited area.
Yeah, what I would say is like, for example, if this is one of the vertex, this is another vertex type, all concentrated.
Right. Then they can be on top of each other almost,
Yeah, so
right?
if this is LL, maybe this is LS, something
Right.
like that. So,
Right.
well, actually, this the other way.
So if our physics ever allows really thick cut windows, Fang, with a sort of scaling inflation concept with your cut windows that, let's say we decide that there's some reason cut windows can sometimes be very big, then we can get really extreme condensations locally of 2 points which had a very long distance in the lattice, hyperlattice, but are literally on top of each other in the lower space, right? Yeah.
Yeah, so it will be like this. This will be LS. This is SL, LS. Just an example, I didn't check. And the middle one, this will be the LL kind of thing.
Right.
Symmetric, in a way. So.
Okay.
Anyway.
But what I understood that you can count this by looking just in the vertical space.
Yeah, that's what Fang helped me to understand too. I didn't deeply get. I got this more clearly than I ever have by you showing those illustrations, Fang. It was worth your.
Yeah, I just feel like when sometimes you may feeling like, oh yeah, but if I draw this picture, you will not forget this picture.
Yeah, well, it's a cookie. It's like sprinkles on the cookie, so I'll never forget.
The one on the left, yes.
Yeah, I want the one on the right because it's more like chocolate chip, big chunks of walnut. More tasty.
That one is like
That's a Christmas.
splattered.
It's a Christmas cookie.
Yeah.
Okay, well, this was good, Fang. Sorry you got sick, but it was good.
Yes. Yeah. Thank you.